want to have a feel of that, you just feel your hair is about 65 micrometer across, and optical fiber is about 125 micrometer across. So thin it is. And how what it has got in such a small, such a thin structure. You have a core of doped glass and cladding of pure glass. Okay, so core in the center, it is surrounded by cladding. So I will discuss all these things as I will go along in this talk. Right. uh, Let me look at where do we use fibers in our lives? Where do we encounter optical fibers in our lives? And let me tell you, without even knowing, we use fiber in several domains of our life. For example, medicine, we use endoscopy, laparoscopy, we use optical fibers in this. Then there are smart structures. Smart structures means that these civilized structures, whether these are flyovers, buildings, railway bridges, okay, there you can install optical fiber sensors, and then they can tell you what is going on in these structures. You can monitor them 24/7, and if there is something happening there, then you can be alerted, and corrective measures can be taken. Optical fibers are also used in cold lighting. For example, these are the pictures from Ajanta caves where plastic optical fiber is used to illuminate the artwork inside, so that you just use visible light, not the heat, because heat may damage artifacts. So you use optical fibers for cold lighting. You can also use optical fiber for personal use. For example, these are the dresses where the optical fiber is embedded, interwoven inside the dresses, and then you can illuminate them with the help of color changing LEDs, and so many things. So, but the most important use, which has affected our lives, which have revolutionized our lives, is telecommunication. So today I'm talking to you because of advancements in optical fiber and optical fiber communication system. Today, everybody is well connected to various platforms on internet, whether it is email, whether it is social media, uh, or whether it is video conferencing like this. So all because of the advancements in photonics technology in general, in wireless technology, and in optical fiber communication system. You see, what I would like to tell you is that it is the combination of optical fibers and mobile communication, wireless communication, that is doing wonders, and that keeps us connected across the oceans, okay, globally. So how it is done? Because you will say that, okay, am I audible, Professor Mohan? It is okay?
Yeah,
Yes,
it's
sir.
okay, sir.
Yes, sir.
Okay, all right.
Okay.
Okay. So you may feel that we use mobile phone for everything, to call our friends, to do WhatsApp, to do email, and so on. But where the optical fiber is coming, we don't see any optical fiber anywhere. So in fact, let me tell you what happens is that, for example, if you are in Hisar in your university, you're talking to your friend in the university itself, then it is basically the mobile tower, local cell tower, which helps you to connect with your friend in your vicinity, in your neighborhood. But if you want to talk to somebody, for example, sitting in Delhi, then what happens is that this local cell tower communicates with this cell tower, and this cell tower is connected with a cell tower in Delhi through optical fiber network, which is carrier core network, and through that basically you then connect to your friend. So it's not only the mobile, but it is the combination of mobile, that is wireless network, and optical fiber network, which is very, very good, and which has basically revolutionized our lives. Okay. Of course, if we just use optical fibers, then it is like using landline phone. We would not like to be hooked with a wire. So we need a wireless. We need optical fiber. Wireless is fine because we don't want to hook to wire. But the problem is that if you use just the wireless link, the data rate is not very good. For example, a typical microwave link can give you 100 Mbps data rate over a few kilometers, over a couple of kilometers. And but if you want to talk to somebody in Delhi, which is much far, then you will have to use fiber optic network, which can give you 10 to 100 Gbps data rate. And today we just not only want to talk to people, but we want to share videos, we want to share pictures, we want to see movies on mobile phone, we want to even see movies on our laptops, computers, even you have these nowadays smart televisions. So everything is through internet, everything is through optical fiber. Okay. So this is fine. Now, if you want to download some data from a computer sitting in New York, then how do we connect to New York with the help of optical fibers? So basically, then there are submarine optical fiber cables. So what I want to say is that it is optical fiber which connects us across the oceans. This is the submarine cable map. So these lines that you see are basically optical fibers. Millions of kilometers of optical fiber is laid on seabed, connecting all of us across the oceans. Well, if we look at fiber optic communication system, so this is a typical layout of a fiber optic communication system where what we have electric signal. This electric signal may come from my voice signal. For example, I am talking to you and you are even seeing me. So there is audio signal and video signal both. And so this electric signal, it modulates light from a laser diode and it generates optical pulses. And these optical pulses go through optical fiber, which is transmission medium. And then at the output end, these optical pulses are converted back into electrical signal using an optical detector. So in this complete system, you would not only require optical fiber as transmission medium, but you will have to do several other things with the signal. You will have to reshape the signal. You will have to filter it somewhere. You will have to switch it. Several operations you will have to do. And so we require several components also. And these components are also in optical domain itself. So signals are processed mostly in optical domain itself. They are amplified in optical domain itself. So, so we need several components for a system. And if these components are available in optical fiber platform itself, then it is much better. And most of the components are now available in optical fiber platform itself, so that they can be very easily connected or spliced with the transmission fiber. And these components are switch, power splitter, multiplexer, demultiplexer, optical amplifiers, pulse shapers, etc. In addition to optical fiber communication system, we also use optical fiber in sensing system. For example, monitoring of civil structures. We can monitor strain, pressure, moisture. We can use optical fibers in biosensors, measuring HB concentration, sugar concentration, detection of virus, and physical parameter sensing, temperature, pressure, displacement, current, chemical sensor, pH, element detection, and so on. So there is a whole domain of optical fiber sensing system. Perhaps there is, I'm not sure, might be a session on optical fiber sensors also. So what I mean to say is this, that optical fiber is used as a not only as a transmission medium to carry signal from one place to another place, but if you want to use it in a system, then you require several components and devices also. And now we have most of the devices and components in fiber geometry itself. Okay? And some of these components you can see here. So either they are made of optical fiber itself, or they are fiber pigtails, so that they can be connected with transmission fibers or other components very easily without much loss. For example, this is 1550 nanometer diode laser, which is used in telecommunication system. It is fiber pigtailed. Then you have WDM coupler. You have amplifier, wavelength filter, optical switch, optical detector, directional coupler, and so on. So there are number of such components which are available. Okay, so in order to understand how light is carried from one place to another place using optical fibers, and how we can use optical fiber to make optical components and devices, let me first go through the basics of optical fibers, and then I will discuss the basic principles behind various components and devices. All right, so let me look at an optical fiber. So it has a core of slightly higher refractive index, and the surrounded by cladding, which is slightly lower refractive index, N2, and then it is protected by a jacket, right? Core is having here 2A diameter. It is about 10 micrometer across in telecom fiber, and cladding is standard fiber as a cladding of 125 micrometer. So if I have A is the core radius, B is the cladding radius. If I look at the refractive index profile of this structure, then from R is equal to 0 to R is equal to A, the refractive index is N1. From R is equal to A to infinity, it is refractive index N2. Although here the cladding is truncated here, but since the cladding is very large as compared to core, we can assume it to be infinitely extended, right? So you have a core of refractive index N1, cladding of refractive index N2, and there is a relative index difference between the core and the cladding, which is defined as N1 square minus N2 square over 2N1 square. Or since N1 and N2 are very close to each other, so we can approximate it to N1 minus N2 over N1. In the fibers where N1 and N2 are quite close to each other, it is known as weakly guiding fiber. And the fiber which is used in telecommunication system, in long haul or long distance communication system, uh, the index difference between the core and the cladding is very small. It is just about 0.3%. So this delta is just about 0.3%. So it's not very large, and it is so because uh, if you have very high refractive index difference, then the pulses do not remain as it is, and they broaden quite a lot, and then the data rate is affected. Okay, so that is why. So in order to have high data rate communication, we need to have this N1 quite close to N2. Fine. How do we send data through optical fiber? It is basically through train of short optical pulses. Okay. So if you send a pulse, this is a pulse in time domain. So this shows basically power as a function of time. So if you send this pulse through optical fiber, then what happens to this pulse when it goes through optical fiber? And so for that, what we require is we need to study how, after all, light is guided through optical fiber. So in order to understand how these pulses will behave when they will go through kilometers long optical fiber, thousands of kilometers long optical fiber, then we need to understand how this fiber guides light. And that is why studying light guidance through optical fiber and the transmission or propagation characteristics of optical fiber are very important. And it will help us, if we understand it, it will help us to optimize optical fiber parameters as per our requirement, whether it is communication system or it is sensing system. Fine. So let us understand how light is guided through optical fiber. For that, let us take a clue from lighted fountains. So if you see these lighted fountains, you can see they are illuminated from the bottom. And if you see this stream of light going up, then this stream of light captures light. Okay. So even if it is curved, So this captures light. We know light travels in a straight line, but these streams of water basically bend the light along it as the stream goes up. You can also do a very simple experiment. You can fill up a bottle with water and let the stream with a pierce a hole there and let the stream of water come out, and then you illuminate it from behind with the help of a laser, and you can see that this stream captures light. It is nothing but this kind of a system has been demonstrated by Daniel Culloden long back. Okay, so how this stream captures light? Well, it is through a very simple process of total internal reflection. We know that when light goes from high index medium to low index medium, so it moves away from the normal. And if we increase the angle of incidence, the angle of refraction will also increase. And at one particular angle, there would be a grazing ray which is coming out, so which is known as critical angle. And if I increase the angle of incidence at core cladding interface, at the interface of these two media, then this ray will come back completely. So this is total internal reflection. And through this process of total internal reflection, optical fiber can also carry light over long distances along all the curves and corners, okay, just like copper wire carries electricity. Fine. So if we look at ray theory and understand light guidance from the point of view of ray theory or total internal reflection at core cladding interface. So here you have the core, here you have the cladding, and there is light guidance through successive total internal reflections. Now these TIR in short for total internal reflection can occur in two ways. One is that when these rays cross the fiber axis, then we call them meridional rays. And there can also be a possibility that these rays go in helical path. Okay, and there is total internal reflection, but they go in helical path. They never cross the fiber axis. So if you look it from the side, then it would look like this. Okay, so these rays are known as skew rays, but guidance through these rays is mostly confined to the periphery of the core or at the near the core cladding interface. So they do not contribute much for light guidance, and we mostly consider meridional rays for light guidance in optical fiber. All right, so now if I look at the longitudinal cross section of an optical fiber, then I can see that there can be various ray paths through which optical fiber can guide light along its length. And the question is, are all the rays are the rays launched at all the angles are guided? And the answer is very simple: no, only those rays which correspond to the critical angle, or which correspond to the angles more than critical angle at core cladding interface, they would be guided. For example, if this red cone corresponds to the critical angle, so Imax correspond to the critical angle here. So if Imax is less than, if I is less than Imax, if I launch a cone of light into this fiber and the semi-vertical angle of this cone is less than Imax, okay, then those rays would be guided. So these red zone that I am showing, it is guided, and all the rays which are larger than this, they will be refracted. So if I launch a cone here, this cone would be guided. A cone of light launched here, which is greater than Imax, it would not be guided, it would be refracted. And so depending upon which cone of light would be guided, I can define the light guidance in optical fiber, and I can see that this Imax, sin Imax, only depends upon the refractive index difference between the core and the cladding. It comes out to be n1 square minus n2 square over n0. It is very simple to do, very simple mathematics. You can very easily do this. And but what I want to bring out here is that the sin Imax is square root of n1 square minus n2 square over n0. And this basically defines the numerical aperture of an optical fiber. Just like you define the numerical aperture of a lens, in a similar way, you can define the numerical aperture of the fiber. It is nothing but it simply tells you the light gathering capacity or light accepting capacity of an optical fiber. As you can see that if you launch light at all the angles, so only this cone would be accepted for guidance, and that is how you will define the numerical aperture. Okay, so by this cone you define the numerical aperture. Fine. All right, so numerical aperture is defined as square root of n1 square minus n2 square. Well, if I go down to understanding light guidance in telecom fibers, so as I've told you that telecom fibers have core diameter which is about 10 micrometer, and the wavelength of light that we use for telecommunication is about 1.55 micron. Okay, so now this core diameter and wavelength of light, they are comparable, and if the wavelength of light is comparable to the dimensions with which the light is interacting with, then our ray theory is not valid. Okay, geometrical optics does not apply there. So then what we will do? Well, then we'll have to consider light guidance in optical fiber in terms of wave theory. Okay, we use Maxwell's equations, for example. Okay, we'll have to use Maxwell's equations, and then we find out how light guidance takes place in an optical fiber. So I am not going into the mathematics of all these things, but in some very simple words, I will tell you how light guidance takes place in an optical fiber and how can we understand it. Okay, so let us have an optical fiber, and if I launch, for example, this laser beam, for example, this laser pointer, light coming out of this laser pointer which you are seeing here, if I launch this light into an optical fiber, so can I predict the pattern, that how this pattern will evolve as the light propagates in this optical fiber? Would would it remain the same? Would I get the same pattern throughout the propagation, or this pattern will change? For example, I take this pattern. This is a spatial pattern now. If I scan the intensity across the diameter, then this intensity is like this. Okay. When this pattern goes through optical fiber, what will happen to this pattern? Okay. Would it remain the same? Or if it does not remain the same, then what will happen to it? Can I say, predict what is the pattern here, what is the pattern here, what is the pattern here? So, so that is very important to understand, because that's how I will be able to find out how, if I launch pulses in an optical fiber, time pulses in time domain, then how would they behave in an optical fiber? And that would be very important for finding out how data can be sent through optical fiber. Well, so as I've talked about, so if I launch some arbitrary pattern, I don't know what this pattern is, and then it is very difficult to tell how this pattern would look like here, 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 or here. It is very difficult to make a correlation between them. However, the wave theory tells me if I solve Maxwell's equations, then wave theory tells me that there are some specific patterns. There are some specific patterns, for example, this pattern, this pattern, this pattern, and many more. Okay, if I launch only those patterns in an optical fiber, then they sustain their shape. They sustain their shape. They are sustained throughout the propagation. There might be a little attenuation. Apart from that, their overall shape is sustained. So this pattern will remain as it is, as it propagates through optical fiber. If I launch this pattern, this will also remain the same. If I launch this pattern, it will also remain the same. So there are certain such patterns which are sustained throughout propagation, and these patterns I call the modes of an optical fiber. So this is one thing, that these patterns are sustained. There are certain such patterns, and also that each pattern propagates through optical fiber with certain velocity, and for different patterns these velocities are different. So these are known as the modes of the fiber. Now this observation that they sustain they sustain their shape and they go with certain velocity. It will help us to understand how an arbitrary pattern will propagate through optical fiber. Okay, well, let me hide this. Okay, now with what velocity these patterns will go, what refractive index, what these patterns will feel. Let us understand that. So for that, let me first take a laser beam. A laser beam which might be, 2 millimeter across or 4 millimeter across. Okay, and let me send it through a block of glass of refractive index n, and this block of glass has 2 centimeter by 2 centimeter dimensions, for example, and this is, let us say, 4 millimeter across. So when this laser beam will go through this block of glass, then this light, this laser beam will have the will go with the velocity c by n in this block of glass. V is equal to c by n. We all of us know this. So this laser beam will experience refractive index of this medium as n. Okay, this is fine. Now let me do the same thing with optical fiber. I know this optical fiber is 10 micrometer across in core size. So this is just 10 micrometer across with refractive index n1. And after 10 micrometer, you have a different material of refractive index n2. Now, if this pattern, which is of course larger than 10 micrometer in dimensions, then if this goes through this optical fiber, with what velocity it will go? What would be the refractive index this pattern will feel, whether it would be n1 or it would be n2. Similarly, now you have another pattern. So what effective refractive index this pattern will feel, whether it would be n1 or n2. Okay, I don't know. But of course, it would neither be n1, it would neither be n2. Okay, but intuition tells me that it would be somewhere between n1 and n2. It would be between n2 and n1. Okay, and for since I can see that the proportion of light in the n1 region and in n2 region is different for different such patterns. So I also feel that this n effective would be different for different such patterns. Okay, so these different modes will travel with different velocities, and their velocities would neither be c over n1 nor would be c over n2, but it would be some c over n effective, where n effective is the effective refractive index felt by or experienced by a certain pattern or certain mode. Okay. Now I have in an optical fiber, I can have two types of modes. One is guided modes. Guided modes means which through which the light is guided, mostly confined in the core region. And then there are other kind of modes uh, through which the light is radiated out. The light is in the cladding and then it radiates out. So you have guided modes, you have radiation modes. For guided modes, the effective refractive index lies between n2 and n1, and for radiation modes, it is less than n2. And since it is less than n2, then uh, the energy radiates out. Guided modes are discrete modes, only discrete patterns, which I have shown you. And but radiation mode, there is a continuum of modes. So any value of n effective below n2 is possible. The very important thing is, that these modes are number one orthogonal, and guided modes and radiation modes together form a complete set. Complete set. What does it mean? It simply means that if you have an arbitrary field distribution, then this arbitrary field distribution can be expressed as superposition of these modes. So understand it, please. That that it means that if you have any arbitrary pattern, if you launch in an optical fiber an arbitrary field pattern, then this arbitrary field pattern can be expressed as superposition of all the guided modes and radiation. Okay, and now each mode would go with certain velocity, and it will sustain its shape. So now if at any value of z, at any value of uh, length of an optical fiber, if you want to know what is the shape of the pattern, then you just superpose all the modes with the accumulated phases, because each mode would go with different velocity, so they will accumulate different phase shifts, okay, as they will propagate through L length of the fiber. So now you superpose all of them with can you please mute? Is it possible? Yeah. Okay. So you just superpose all these modes with the accumulated phases, and the result and find out what is the resultant pattern. That would be the pattern that you will get at any value of Z in an optical fiber. So this is how you can find out the evolution of any arbitrary field pattern with the help of these modes. Now let me just show you some of the patterns, and the question, a very important question now arises: how many such patterns are there? How do I know? How do I know whether my fiber will have two such patterns, three such patterns, or 10 such patterns, 20 such patterns, and what kind of fiber is useful for my application? Less with less number of patterns, or less number of modes, or large number of modes. Okay, so let us understand it. Okay, so if I have in a fiber, I now have three things. Number one, N1, number two, N2, number three, core radius. So refractive index of core, refractive index of cladding, and the core diameter of core radius. These three things from an optical fiber. And fourth, very important thing is the wavelength of light itself. Okay, so all these things will affect the number of patterns which are supported by an optical fiber, and how do these patterns look like. Okay, so all these things will affect it. So let me do one thing. Let me fix the material of the core and the cladding. So let me fix N1 and N2, and let me fix the wavelength of light, okay, which I am propagating through optical fiber. And let me vary the core radius. Okay, if I, for example, take A is equal to 20 micrometer, then I see several such patterns. If I reduce A from 20 to 15 micrometer, the number of patterns are reduced. There are Here you had 7, now I have 4, 2, and at A is equal to 8 micrometer, I get only, say, one pattern. Okay, so what I see that for all the other fixed things, N1, N2, and lambda, if I reduce the core size, then I reduce the number of modes. So one observation. Now let me fix the value of N1 and A and just vary the value of N2. When I vary the value of N2, it means that I am varying the value of NA. NA is defined as square root of N1 square minus N2 square. So I could have written only N2 also here, but I prefer to use NA here, because when you buy an optical fiber, so they write that this fiber has this much of Na. They will never write that it has this much of N1 and this much of N2, but they will write that this is the Na. Fine. So now when I see the number of patterns which are supported by an optical fiber, so at Na is equal to 0.4, that is high refractive index contrast. I have 7 patterns. I reduce Na to 0.3. I reduce the number of patterns to 4, and at Na is equal to 0.2, I get only one pattern. So if I reduce the core cladding index contrast or numerical aperture of the fiber, then also I reduce the number of modes. So the number of modes reduces with A, and number of modes reduces with NA, or refractive index contrast. Fine. Now, what is the effect of wavelength? Is there any effect of wavelength of light also on the number of modes supported by the fiber? Well, for that, let me do a very simple experiment. Let me take a tunable light source, or I take lasers of different wavelengths, okay? And I launch light into an optical fiber, which has given optical fiber, which means that I have N1 and N2 and A, which are fixed. I launch light into this fiber using some optics. MO means microscope objective. And output of the optical fiber, let me image with the help of an MO over a CCD. Okay, so as soon as this light comes out of an optical fiber, I image it with the help of an MO. I don't let it diffract too much. Okay, fine. So when I see the CCD output, and what I'm doing, I am varying this wavelength. Okay, so let me first launch wavelength, light of wavelength 200 nanometer, and I see the output of, which is given, which is recorded on CCD. So it looks like this. You see several, grains here, several spots here. This is known as a speckle pattern, and in fact, this is a superposition of 39 modes. So 39 such patterns, 39 patterns which I had showed you earlier. Okay, so it is a superposition of 39 modes. Now what I am doing, I am slowly increasing the wavelength of light. Now I have got 250 nanometer, and as I change the wavelength, this pattern changes. You can see the size of the spots here, speckles here, it increases. This green size increases. Okay, 500 nanometer, 600 nanometer, 700, 900. At 900, what I see, it is just the superposition of two such patterns. And if I go along 1200, 1500, at 1500, I see very clean pattern. Okay, there are no speckles. Okay, very clean, uniform pattern. And so this is only one mode. This is only one mode. So what I see that as I as I increase the wavelength, the number of modes decreases. So now I have three things. One is the number of modes. The number of modes increase as you increase core radius. The number of modes increase as you increase numerical aperture. The number of modes decrease as you increase lambda. So the number of modes depend on all these three things. And fortunately, if you do the analysis of an optical fiber, very naturally and very nicely, all the three parameters are integrated into a single parameter, okay, which is defined like this: 2 pi over lambda naught times A times NA, is numerical aperture. So all the three parameters are now there in a particular combination, and this combination is known as normalized frequency. Normalized frequency because lambda is appearing downstairs here in the denominator, and it is normalized. It does not have any dimensions. Okay, A has the dimensions of micrometer, lambda has the dimension of micrometer, and it does not have any dimension. So that is why it is known as normalized frequency. So you can write it like this or like this. So it will depend upon what do I see, that it depends upon V. Okay. So as you can see that with A and NA, the number of mode increases. So A and NA, they appear in the numerator, and with lambda naught, the number of modes decrease. So it appears in denominator, right? And rigorous analysis shows us that if V is less than a particular value, which is 2.404, this is a magic number somehow. Okay? It comes out from mathematics. It is basically a zero of a Bessel function. So you need not to go into those details right now. So just take my words that if V is less than 2.4048, then fiber supports only one mode. Okay, and then it is known as single mode fiber. Okay, so we need to remember this number. Okay, so if V is less than 2.4048, only one pattern goes through an optical fiber. Okay, one pattern is sustained, and it is single mode fiber. If V is much larger than 2.4048, we call it multi-mode fiber. And for intermediate values between this and this, we have few mode fiber, which is a terminology which has appeared or which have got popularized very recently from the point of view of potentially new generation optical communication system. Well, so If I talk about now single mode fibers, single mode fiber is used in long haul optical communication. It has a small core diameter, about 10 micrometer, generally uses laser diodes as light source. Coupling light into this fiber is critical because it is very small, core size is very small, so you need precision equipments, but nowadays everything is well standardized, okay, and you have all these things available. Okay, joining two fibers is a bit critical, but nowadays you also have very good splicing machines available. With the help of those splicing machines, you can join two fibers together without much loss at the joint. Okay. Typical parameters of silica glass single mode fiber are delta is about 0.3%, which corresponds to numerical aperture of about 0.1, and core radius is about 5 micrometer. So this is a single mode fiber, which is used in telecom system, long haul telecom system. Now the multi-mode fiber. Multi-mode fiber is suitable for local area network where you need to just have a communication over very small distances, and you it has core diameter of about 50 micron. You can also use light emitting diode in such kind of systems, and coupling light into it is easier because its core dimensions are much larger, and therefore system equipments components are also less expensive. If I talk about typical parameter of a silica glass multimode fiber, its delta is about 1%, and numerical aperture correspondingly is 0.2, core radius is 25 micrometer. If you buy a single mode fiber and a multi-mode fiber from a market, okay, if it is not jacketed, not color coded, you won't be able to make out a difference between the two because the overall diameter of the fiber, the cladding diameter of the fiber, in both the cases is 125 micrometer only. Okay, but if you launch light into an optical fiber, then only you will be able to find out whether it is a single mode fiber or a multi-mode fiber. You launch light in a single mode fiber and image its output, look at its output, then it would look like this. If you launch light into a fiber which is multimoded at this wavelength which you are launching, then you would see such kind of pattern. So this is the output from a multimode fiber. You can see these speckles. These are from my laboratory itself. Okay. All right, so till now the fiber that we have seen, it had uniform core refractive index, uniform cladding refractive index. So if you look at the core refractive index, it is uniform, cladding refractive index, it is also uniform, and you see a step kind of thing. So it is known as, excuse me, step index single mode fiber. Okay, step index single mode fiber. You can also have a fiber whose refractive index, for example, in core changes with position. For example, like this, then it is graded index single mode fiber. Okay. You can also have a step index multimode fiber and step index graded index. Graded index multimode fiber. Okay. So these are some kind of fibers which are available. All right, now let me talk about data transmission through an optical fiber and the bitrate requirement for some common information containing signals. For example, you see, you you write messages, you send emails, you send text, you send your voice signal. Basically, you talk over telephone, mobile phone, or even on internet. Okay, you browse through books, encyclopedia, you see television on your mobile phone. Okay, so you use various services. You use various services, and for these services, if you look at typical bitrate requirement, then it is like this: 1,000 words of text, about 60 KB. Telephone communication, 64 kilobits every second. 20 volumes of encyclopedia, 300 MB. Standard television, you need 100 megabits every second. High definition television, 1.2 gigabits per second. So this is the kind of, some are dynamic signal here, and here, and some are static signal, of course. That is why there is somewhere it is data rate and somewhere total data given. Anyway, So you see that for various services you require, you need to send data through your communication system at a particular rate. Okay, otherwise this cannot be sent uh, uh, nicely. Well, if you look at mobile phone network, okay, microwave communication, so it gives you a data rate of about 100 Mbps over a few kilometers. Okay, and with this data rate, if you want to send video signals, okay, then it would be much difficult. Okay, however, if I use optical waves for communication instead of microwaves, now I use optical waves as carrier. Then, since the frequency of optical waves is 10 to the power 5, 10 to the power 6 times the frequency of microwaves, so you are increasing the frequency of carrier itself, so you increase bandwidth also. Okay, so you increase bandwidth. So with the help of that, you can send all these data uh, uh, with uh, with considerably high rate through your optical communication system, through your communication system. So basically, how do you send data? Whatever data it is, whether it is text, telephone, or TV, or picture, whatever. Ultimately, you convert it into binary. So it is basically a sequence of zeros and ones. This sequence basically contains your data, and you need to just send these zeros and ones through your optical fiber, right? So as I've said that if you use optical frequencies, then there is tremendous increase in the information carrying capacity of a communication system compared to radio waves or microwaves. That is why we use optical communication system. And since we need to now carry optical signal over large distances, without getting affected from environment and other external things. So we need an optical fiber, and through optical fiber we send data in the forms of zeros and ones, and the zero is basically no light pulse and one is high light pulse, so high and low light pulses, so in the form of light pulses. Fine. So we send data in the form of optical pulses. So this is input optical pulse train. This is power versus time. So it is in time domain and it goes through optical fiber. Now what happens to these pulses? What happens to this pulse train when it goes through optical fiber? Would I get the same pulse train at the output after even 10 kilometers, 30 kilometers, 50 kilometers? If I could, then nothing like it. Then all our problems would have been solved much easier. But unfortunately, this does not happen. When you send this pulse train, it becomes something like this. Okay, it does not retain its original shape. Okay, because of various effects, through which this pulse train undergoes in an optical fiber. Okay. All right, so what do we see here? That these pulses get attenuated, their power level go down, and they also broaden in time. Okay, and the thing is that if there is considerable attenuation or too much of broadening, then if there is considerable attenuation, then my detector will record zero everywhere. Okay, it will not be able to distinguish between zeros and ones. Okay, then my data is lost. Okay, information is lost. On the other hand, if the broadening is too much, then all the ones merge into each other. Okay, then I won't see any zero anywhere. Okay, then also, so if what I mean to say, if these pulses broaden so much that they overlap, okay, they overlap too much, then also I would lose the information because I won't be able to tell where the one is, where the zero is. Okay, so before my output pulse train reaches to this kind of shape where I lose information, I need to get back the original shapes of the pulses. That is, I need to do signal processing. I will have to reshape the pulses, reshape the signal, and that is done in repeater. Okay. So what is important is repeaterless transmission length of the link. Okay, longer is this length, less costly your system is, because then you will have to employ less number of repeaters. Okay, so this is a very important parameter of a communication system, the repeaterless length of the link. And it of course depends upon how much is the attenuation in optical fiber, how much the pulses get attenuated, and how much the pulses get dropped. Okay, fine. If I talk about attenuation, attenuation is described in terms of dB per kilometer. So it is 10 log 10 P in over P out. I'm sure you are aware of this terminology of dB. And so let me look at the attenuation in a silica glass fiber, which is the fiber used for telecommunication system. Okay. Now I will have to look at what is the wavelength dependence of this attenuation. So does this attenuation remain the same at all the wavelengths? Okay, so can I use any wavelength in an optical fiber for telecommunication? Or there are some specific wavelengths at which the loss of an optical fiber is quite small, and then I will prefer that wavelength. Fine. So for that, I look at spectral loss variation in fused silica glass, and this is from 1979. Although nowadays the fiber which is available, it does not have this kind of spectrum. I will show you that also. But this kind of spectrum is useful to study because it tells you almost most of the effects through which the attenuation occurs in an optical fiber. Okay, so let us look at this and analyze it. So what I see that there is one trend like this, another trend like this, and then there are few peaks there. If you look at this trend shows that as wavelength increases, the loss in an optical fiber goes down. Okay, this is nothing but Rayleigh scattering loss, which goes as 1 over lambda to the power 4. Fine. If you look at this is nothing but the tail of absorption peak in silica glass, which occurs at around 2 micrometer wavelength. Okay, around 2 micrometer. So it is just a tail of that. So here if you go to shorter wavelengths, your Rayleigh scattering loss increases. If you go to longer wavelength, your infrared absorption in silica increases. Okay, which comes from the material itself because of the energy bands and energy levels of silica itself. Okay, all right. So which means that in between you would have some wavelength where you will have less loss. Let us talk about these peaks now. This huge peak and this peak are basically due to moisture in the glass which is used for telecommunication. Okay, so for making optical fiber, these are OH ion peaks. These are OH ion peaks, also known as water peaks. These small peaks are due to other impurities, right? And here I see that there is a wavelength at which is 1550 nanometer where the loss is minimum. And that lowest loss is 0.2 dB per kilometer. And that is why this is the wavelength which is optical communication window. So around this window, we prefer to use optical communication. There are various loss mechanisms. Let me see how much I can go through it. So very quickly, I can just summarize these, that I can divide these loss mechanisms mainly into absorptive and radiative. And in absorptive, there can be absorption due to primary constituent material of the fiber, which is silica glass. Then it is called intrinsic. Losses due to absorption by impurities, that is extrinsic. That includes water peaks also. Then there is Rayleigh scattering loss. This is radiative. Okay, why Rayleigh scattering loss occurs? Because during the process of fabrication of fiber, very small scale inhomogeneities, wavelength scale inhomogeneities, they got frozen in the fiber at the time of fabrication. Okay, fine. And nowadays you have a fiber whose loss spectrum looks like this. So you can see all the impurity peaks and water peaks, they have now gone down. So what I see is basically this trend Rayleigh scattering, and then if you go much above this, then there would be infrared absorption. So this is low water peak fiber from Corning glassworks. Okay, so here are various typical loss values at various wavelengths. So at 1550 nanometer, you can see the loss is about 0.19 dB per kilometer. These are various communication bands. Uh, the first one is 850 nanometer, around 850 nanometer, which has loss of 2 dB per kilometer. Second is 1300 nanometer, which is 0.5 dB per kilometer. And third is 1550, which is zero point 0.3. It is now even less than that, zero point 0.2 dB per kilometer, or even less. Okay, so you have various such bands, and these bands are also labeled as S, C, L, and U band, short, conventional, long, and and this plot very nicely shows these three bands: 850, 1300, and 1550 nanometer. Okay, in terms of attenuation, where we are going ahead, where we are heading to, uh, well, uh, we have seen that at 1550 nanometer wavelength, Rayleigh scattering loss has come down quite a lot, and infrared absorption peak has not taken has not taken up. So we have very small loss. Okay, if I go down to, for example, 2 micrometer wavelength, instead of 1550 nanometer, if I go down to 2 micrometer wavelength, then Rayleigh scattering loss would be even very small. It would be very, very small. Okay. And the only problem is that at 2 micrometer wavelength, IR absorption loss would be very high. So if I use silica glass fiber, so if I use silica glass fiber, then I cannot use light of wavelength 2 micrometer. Okay, although the Rayleigh scattering loss can be very small. So can I use some other material? Can it be done? So, and what are those other materials? So the answer is yes, you can use fluoride glasses, for example. And for fluoride glasses, the IR absorption peak occurs at about 50 micrometer wavelength. Okay, and at 2 micrometer wavelength, the loss is 0.01 dB per kilometer. Just look at it. That silica glass fiber has lowest loss wavelength 1550 nanometer, and at this wavelength the loss is 0.2 dB per kilometer. If I use fluoride glasses and use 2 micrometer wavelength, the losses will come down to 0.01 dB per kilometer. Okay, so which means that I can increase repeater spacing more than 1000 kilometers, which is typically 50 to 100 kilometers for silica glass fibers. Okay, so I can have considerable increase in repeater spacing. But the problem is that you need to have sources at this wavelength available, detector at 2 micrometer, then amplifiers at 2 micrometer. So all these things have to be established, and so that this can uh, be used. 2 micrometer can be used. Okay. All right. So now let me look at pulse broadening. So I have taken care of attenuation. Now what happens is that if I send this pulse train and they broaden in time, and if the broadening is not too much, then I will be able to distinguish my zeros and ones. Okay, and information is there. But if the overlap between, if the broadening is too much, then the overlap between the pulses is like this, then everywhere I will record only one, and the information would be lost. Okay, and the question is what causes this broadening of pulses? And there are two mechanisms. One is intermodal dispersion and another is chromatic dispersion. Okay, what is intermodal dispersion? It is basically if you have a multi-mode fiber, then you have different ray paths. Okay, you have an axial ray which will travel, which will reach the output end very quickly because it has the shortest path. And then you have other rays going at different angles, they will take longer path. So when you launch light in an optical fiber, all these ray paths can be excited, and light can go to output end through all these ray paths. So there would be broadening. Okay, although you can minimize this broadening to certain extent by using graded index fiber, but still, if you want to use the fiber for long haul communication system, then it is better that you use a fiber which does not have many modes, has only one mode, and that is why single mode fiber is used for optical communication system. Fine. So we can take care of intermodal dispersion if I use single mode fiber. Okay. In single mode fiber, what happens? So is there dispersion there also? Okay. Is there broadening in single mode fiber also? Yes, there is broadening in single mode fiber. Now, why there is a broadening in single mode fiber? It is because of chromatic dispersion, different wavelengths. Now you will ask from where the wavelengths are coming, different wavelengths are coming. We are using a laser source. Laser is monochromatic. Yes, laser is monochromatic, but it has a certain degree of monochromaticity. Okay. It still has a line width, okay, delta lambda. Okay. So what I mean to say that if I say laser of 1550 nanometer wavelength, it is not strictly 1550 nanometer wavelength. Okay. It has light, it has wavelengths, let us say from 1549 to 1552 or 1549 to 1550. Okay. Maybe 1 nanometer width, 2 nanometer width. But this 1 nanometer or 2 nanometer line width is sufficient to 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 broaden the pulses because you are taking data over kilometers length of the fiber. Okay, what would be the consequence of having several wavelengths even in a very small line width? Okay, the consequence is that if you have different wavelengths, then these different wavelengths will have different refractive index of the material. Okay, because the refractive index is wavelength dependent. We have seen in prism. Okay, in prism. So prism is made of glass. Okay, and if you shine white light through it, it splits light into several colors. Okay, all the constituent colors. All right. So because why? Because the refractive index of glass is different at different wavelengths. That is why there is a splitting. Okay. So similarly, glass fiber also, it is made of glass. So different wavelength components will go with different velocities, and so there would be broadening. This is one thing. Second thing is the mode of the fiber itself. The mode of the fiber itself will have different propagation constant or different velocity at different wavelengths, and that is why there is broadening. So even in single mode fiber, you have broadening due to chromatic dispersion, and we have to take care of that. All right. So with this background and with these requirements that we have to address for optical fiber communication, because ultimately we have to have more repeaterless spacing, we have to have less attenuation, and if there is attenuation, we need to amplify it. We need to have less dispersion. If there is dispersion, there is broadening, we will have to compress the pulses. So there is a requirement of optical fiber devices and components. And these components, as I've already listed earlier, switch, power splitter, filter, multiplexer, demultiplexer, amplifier, and so on. So let me look at these components one by one and see how much I can cover. So the very first component or device that I would like to discuss is directional coupler. And this is a very important device or component uh, because it is a building block of several other devices. Okay. How? It is basically a 4-port device. And so you have port 1, port 2, port 3, and port 4. Okay, it can act as a switch. So if you, depending upon its characteristic and depending upon, I will tell you the interaction length. Okay, this is basically made by bringing two waveguides or two fibers together. This is 1 to 2, it is basically one fiber, and 3 to 4, this is another fiber, and they are brought quite close to each other. Okay, well, so what you can have here, that you launch light in this port and light comes out of this port. So there is cross. Okay, there is coupling from one fiber to another fiber. Then it acts as switch. Another possibility is that you launch light into this and the power gets split in equally in port 2 and port 3. Then it is power splitter, 50-50 splitter, 50-50 directional coupler, or 3 dB coupler. Another possibility, you launch light of two different wavelengths into one port, and at the output it comes out of different ports. So then there is demultiplexing. Similarly, if you operate it from the other side, you launch light of lambda 1 frequency from port 2, lambda 2 from port 3, and then both the wavelengths will appear from port 1, then it is multiplexed. Okay, how does it work? It is basically a very simple thing. You just bring two fibers cores very close to each other. The cores of two fibers you bring very close to each other so that they interact. Okay, they are not now independent cores. Then what happens is that if you launch light into one core, then it slowly goes into another. Okay, you can see, and then okay. So the power gets switched from one core to another core. Okay, so this is how a directional coupler is defined. And so this is one fiber core, this is another fiber core. We launch light into one and it will slowly come out of the other. What happens is, what is the physics behind this? Understand it. Just look at this. When the cores are well separated, this is core 1, this is core 2. Okay, so this is the mode of core 1 individual core. This is the mode of core 2 individual. So what does it mean? That if you launch this pattern, this amplitude pattern of light, it will go as it is. In this core, you launch this pattern, it will go as it is. So these are the modes of the system. Okay? But when you bring these codes together, then now this one is not the mode of the system. Now, what is the mode of the system? Mode of the system is now this. Basically, what happens is, when you bring them together, then these two amplitude patterns you can combine. Okay? And combination of these two patterns will form the modes of the composite structure. Okay? You can combine them like this. When the peaks of both the patterns are on the same side, then it is known as symmetric mode. When the peak of one is on the other side, then it is anti-symmetric mode. So in the opposite sides, when the peaks are in opposite sides, then it is anti-symmetric. So what does it mean? That these are now known as normal modes or super modes of the system. So this is not, a single peak pattern is not the mode of this system or this system, but double peak pattern with two peaks on the same side and two peaks on the opposite side, they are the modes of the system. So this will travel as it is with certain propagation constant, and this will travel as it is with certain propagation constant. They will not change with their shape. These are now the modes of the system. So if I launch light into this structure and I want to understand how this light will behave as it will go through this structure, then I will have to split that pattern into a combination of these two modes, and then only I can study. Let us understand. Okay. So this is the composite structure now, and I launch light into core 1. Okay. Launching light into core 1 can be considered as exciting the anti-symmetric and symmetric super modes equally, like this. So if you take the superposition of these two modes, let us say at z is equal to 0, then this and this will add up. So you will have light here, and this, they will cancel each other, so you don't have any light here. So this is exciting. Excite Launching light into one core is basically exciting the symmetric and anti-symmetric modes of the system equally. Now what will happen? Now, the propagation of light in such a structure, I can understand in terms of propagation of these supermodes. So this mode will go as it is, and it will reach here. Okay, this mode will also go as it is, and it will reach here. But what will happen that when they will go, this will go with certain velocity, this will go with other velocity. So as they will traverse length, let us say L of the fiber, of this system, then there would be a phase shift accumulated between them. And let us say after length LC, the phase shift between them is pi, which means that if I consider this as it is, then this one will flip. This one will flip, okay, after length LC. So this I have considered as it is, and this one will flip because of pi phase shift. Okay, there would be some constant phase also associated with both of them, but the difference of pi phase shift will give you, if one is like this, then other one will be shifted. Now if you superpose them, then they will cancel, and there would be a resultant pattern in the waveguide too. Okay, so if you launch light in core 1, then light will slowly get coupled into waveguide 2 and then waveguide 1, then there would be periodic coupling of power from waveguide 1 to waveguide 2. So this is how a directional coupler works. Okay, I can explain this with the help of a very simple thing, and that is a coupled pendulum. Uh, so, so here what I have shown, here I have shown the reflective index profile of a directional coupler. So this is core 1, this is core 2, and this is the symmetric mode where the peaks are on one side itself in both the cores. Okay. So if I launch this pattern, then it will go as it is. It will not change its shape, and it will go with certain velocity or certain propagation constant. Similarly, this is anti-symmetric super mode. So the peaks are on the opposite side. So this will also go as it is without any change in its shape. I can explain this with the help of a coupled pendulum. Okay, how? Let us take this coupled pendulum. So I have two bobs here. Okay, you hang them with the help of these two strings and then couple them. Okay, tie them up with the help of another small string. Okay, so that's how you couple them. So you have orange one here and green one here. Okay, now what are the modes of this coupled pendulum? Just try to understand. So what you do for this, you push both these bobs, orange and green, away from you simultaneously and then release them. Then what if they will do? They will do oscillation. There would be oscillations like this, that both of them will go away from you simultaneously, and then both of them will come towards you simultaneously. Okay, so then there would be these kind of oscillations, and these oscillations will go on forever if there is no air resistance with certain time period. So this is symmetric mode of coupled pendulum. Okay, so this pattern that both of them are going away from you simultaneously and coming towards you simultaneously, this is one mode of the system. And time period, it is analogous to the propagation constant of the mode. Okay, this is one thing, symmetric super mode. Now what you can do, you can pull orange one towards you and push green one away from you. Okay, and then you release them. Then they will do oscillation that when one is coming towards you, another is going away from you, and in this way they can oscillate, and they will also oscillate forever if there is no air resistance. So this is another mode of the system, which is anti-symmetric super mode. Now what you do that you just displace one of them. For example, orange one. So just pull orange one towards you. Green one would be in the mean position itself, there itself, and then you release the orange one. Basically, then you're putting energy to orange one. then what will happen? You will see that initially the orange one is in full swing, and slowly this will transfer energy to green one. Green one will start oscillating slowly, and you will see that after a certain time, orange one will stop and green one will be in full swing. So it has transferred its complete energy to green one. Then green one will stop and orange one will again be in full swing, and so on. Okay. So this I can show you with the help of some simulations, and also with the help of some movie which I have made. I hope it will work here. Let us see. So this is the symmetric super mode, simulated one. You see the changing color. Changing color means that as it goes in Z direction, as it propagates through this structure, okay, then it is not changing its shape. Okay, so different colors means the profile at different values of Z. So you can see color is changing, but its pattern is not changing. This is symmetric super mode of the structure. Okay, let me see if I can play this. Unfortunately, it is not working in this. Okay, I'm sorry, it is not working here. Maybe I can share the movie in some other platform. Well, so you can do this. So you can see I have made these with the help of just two nuts. You can take anything. There was lockdown, so when I made this, so whatever was available at home, I have just made it using that. And so you can just displace both of them in one direction and then release them. Then they will oscillate like this. Then one in this direction, another is this direction. Then you will have anti-symmetric super mode like this. Okay, and when you will just put energy into one, then you will see that there would be periodic coupling from one waveguide to another waveguide. Okay, all right. So this is how you see that power in one waveguide, it will go down. Power in another waveguide, it will increase. Right, and so you see that after certain length LC, there is complete switching of power. Okay, and this length LC will depend upon what is the strength of interaction between the waveguide. Okay, and that is measured in terms of coupling coefficient kappa. So at Z is equal to pi over 2 kappa, which is LC, there would be complete transfer of energy. Okay, all right, and you see, so at this value of Z, which is Z is equal to LC, it will work as switch. If you operate it Z is equal to LC by 2, then there would be 50% power in core 1, 50% power in core 2. Then it would be 3 dB coupler or 50-50 coupler. You can choose any other length to have desired ratio of splitting. So you can have it as switch, you can have it as power splitter. Now, this coupling coefficient is wavelength dependent also, and if you satisfy certain conditions, okay, if you satisfy certain conditions, which is kappa 1L, that is if your length of interaction is such that kappa 1L is m pi and kappa 2L is m plus half pi, then what you can have that if you launch both the wavelengths in this waveguide, then this wavelength will appear here itself, because for this wavelength kappa 1 times L is m pi, so it will not switch to another one. While for lambda 2, since kappa 2L is m plus half pi, then it will switch to another one. So you can have demultiplexing. Similarly, you can have multiplexing. Okay, so this is multiplexing. The previous one was demultiplexing. All right. So this was directional coupler, and now you can also have periodic structures in the core of an optical fiber, and you can basically have gratings. Okay, periodic structure in the core of an optical fiber. So what happens is basically, let me show from this picture that if you have the core of an optical fiber and you have periodic refractive index modulation here somehow. Okay, I will show you how you can get it. So I'm sorry, this arrow is not correct. So lambda goes from this to this only. All right. So this is the pitch. This is the pitch of the grating. So, and this refractive index difference here between this and this, okay, this high index segment and low index segment is very, very small. It is of the order of 2 into 10 to the power minus 4. So it just acts as perturbation. It would not affect the propagation of mode. Okay, it would not affect the mode of the system, but it will just affect the propagation of mode. Well, it will not affect the propagation of mode. So now in the absence of this perturbation, this fiber, if you launch light from this side, so light will go only in this direction and forward direction. So you will have only forward propagating mode. By no means you can couple light from forward propagating mode to backward propagating mode. Okay? In an ideal fiber, in an ideal situation, because there is no mechanism. Light you have launched in this direction from left to right. So it will keep on going from left to right. Okay. It will not start going from right to left at its own. So it will not go in this direction, this mode. Okay. However, if you have a perturbation like this, okay, so this is the wave vector for propagating light in forward mode, okay, forward direction. This periodic perturbation can give you a wave vector in this direction if the length of this wave vector is such that uh, the the length of these two together and length of this is the same. Then your light is going in this direction, and then this wave vector takes it from here to there. Okay, which means that light can now get coupled from forward propagating mode to backward propagating mode if this condition is satisfied. If this condition is satisfied, okay. So 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 this is the Bragg condition for fiber Bragg grating, and this condition will be satisfied only for a particular combination of lambda b and n effective. Understand it, that that you have launched light in forward propagating mode, and this perturbation causes coupling of light from forward propagating mode to backward propagating mode. Okay, if this phase matching condition is satisfied, that is, the magnitude of k is 2 pi over capital lambda, is equal to twice the magnitude of one of the propagation constants. So So twice the magnitude of this, 2 times beta. Beta is 2 pi over lambda b n effective. So 2 times beta is equal to k. So this gives you lambda b at which this condition is satisfied. Okay. Typically, if you take optical fiber, n effective is 1.5. Okay, and lambda b, if you take 1.5 micrometers, so capital lambda is zero point 0.5 micrometer. So this periodicity is just 0.5 micrometer. Okay, this is fiber Bragg grating. What happens is, in this kind of grating, that if you launch a broadband spectrum, then what will happen, that one wavelength which satisfies this Bragg condition, then that will get reflected. Okay, so in reflected spectrum you will see this, and in transmitted spectrum this would be missing. Okay, and this width of this, okay, width of this reflected spectrum, delta lambda, is very, very small. It is about 0.1, 0.2 nanometer only, because a phase mismatch is very large. So phase matching condition is very critical. So this delta lambda is very small here. Okay, so as soon as there would be a little deviation from this lambda b, the intensity of reflected light will come down drastically, because phase matching is not there now. Okay, this is typical reflection spectrum. So this is how the reflection spectrum looks like. So you have this peak along with these side lobes, and typical delta lambda I have shown 0.2 nanometer. Okay, let me not discuss this because time is already over. I would like to discuss the applications of fiber Bragg grating. So one or two such applications. One application is optical add drop multiplexer in telecommunication system. What it is, if you have a telecommunication system and you are launching three wavelengths, for example, lambda 1, lambda 2, lambda 3, blue, green, red. Okay, all these wavelengths in a WDM wavelength division multiplex system can carry data independently. Okay, at some point of time, for example, you want to drop red wavelength, then what you can do, you can make a combination of FBG, fiber Bragg grating, and circulator, and you can drop this wavelength. How? So red wavelength, it will go like this, and the periodicity of this grating is so chosen that it will reflect red one. So red one will now be reflected from FBG, and the circulator will guide it to this drop port. Okay, it will be dropped. If you want to add, for example, red wavelength at certain point of time, then again you can use FBG and circulator combination, and you send red wavelength from here. This circulator will guide it to this port, so it will go like this, and then it will be reflected from FBG, and it will go like this. It will be added. This is one thing. Second thing is that you can use it for strain sensing. What happens is that the Bragg wavelength depends upon, we have seen that it depends on capital lambda and n effective. Okay, so this strain can change capital lambda and delta n, and so the Bragg wavelength will change. So as the strain will be there in the structure, FBG will get strained and your Bragg wavelength will shift. By measuring this shift, you can estimate the strain in the structure. Typical strain sensitivity, you can have 1.2 picometer per microepsilon. Similarly, temperature variation you can sense with the help of this. If you change temperature, it will change capital lambda, that is pitch of the grating, and delta n. This will also cause shift in Bragg wavelength, and you can do temperature sensing. Typical temperature sensitivity, you can have 10 picometer per degree centigrade. This is a typical commercial system which is used for monitoring civil structures like flyovers, buildings, railway bridges, where what you can do in the same fiber, which can be kilometers long, you can have different gratings inscribed, and each grating has different periodicity, so they will have different Bragg wavelengths. So, for example, if you want to put it on 1 kilometer long flyover and want to monitor the strain in the flyover at every 100 meter, so every 100 meter you can have a grating, and then you can monitor these Bragg wavelengths, and you can see which Bragg wavelength is shifting. If lambda b5 is shifting, then you can find out, okay, at 500 meter from the initial point, there is something happening in the bridge. Okay. All right. How much time do I have? Do I have 10-15 more minutes, or
Sir, I think
it's already
the
over?
lecture is getting quite hectic. For 90 minutes is a long time to me, but
Okay. Okay.
and
So
participants. So I think
It
we
has
can
been very,
have
I'm finding
once
it very
again
interesting.
your lecture in the second part of is
okay.
quite interesting, where you started the application part.
Yes.
So I think
Okay.
you can
In
conclude with
five,
two, three
7 minutes,
important
I will
points.
conclude.
Yeah,
Okay. Okay.
yeah.
So all right. So let me skip this, and what I will do is basically I will come to. All right. I will come to this. Okay. So what I have skipped is basically optical fiber amplifiers. Just to tell you a little bit about the optical fiber amplifiers, you see that if you want to amplify signal, then it is not good that you convert first the optical signal into electrical and then amplify with electronic amplifier and then convert it back into optical. Rather, you can amplify signal in optical domain itself by using the principle which is used in lasers. Okay, in lasers, what you do, if you look at the full form of laser, what is the full form of laser? Light amplification by stimulated emission of radiation. Okay, although in lasers you don't see any input signal. Okay, there is only output. So laser is in fact an oscillator because there is a feedback due to mirrors. Okay, but the same process you can use for amplify signal in optical domain itself. Okay, and that is done in erbium doped fiber amplifier. So you have a fiber whose core is doped with erbium, and these erbium ions can amplify signal at 1550 nanometer wavelength by the process of stimulated amplification. Okay, so that I have skipped. What I have now come to is almost my last 2 3 slides. I'm sorry it has been too heavy for you. So this is the futuristic system where we are heading to actually. So if you look at the capacity of optical communication system over the years, how it got evolved. So, so it can be summarized in this trend, which is shown by this blue line, which is a trend that every 4 years, the capacity gets multiplied by a factor of 10. So there's a tenfold increase every 4 years. This has been trend until recently, and we could keep up with this trend with various advancements, initially improved transmission fibers, then erbium doped fiber amplifier, then WDM system, then high spectral coding. But now we have reached to a level where our available fiber and available systems, WDM, DWDM systems, we have exhausted all these things, and now it has got stagnant. Okay, at this limit, which is about 10 to the power 14 bits per second or 100 terabits per second. Okay. On the other hand, the demand for bandwidth is increasing day by day. Okay. If you look back 5 years ago, not so many people were watching television on mobile phone, but now several people are watching television on mobile phone. People are using smart TV and so on. Okay. Now, if we want to keep up with this trend, then we will have to now do something different. Okay, we cannot just rely on whatever fibers are already there. Okay, so we need to do something different, and now people are looking at a different domain itself, which is SDM, space division multiplexing. Wavelength division multiplexing we have exhausted. Now it's time for space division multiplexing, and for that you can use multi-core fibers. That is, you have several cores shared by the same cladding, and each core can carry data independently. You can have coupled core fiber. I'm just telling you a few possibilities here, not all of them. You can have coupled core fiber, so where the cores are coupled and super modes of these cores can carry data independently. And third is few mode fiber. Few mode fiber where you have just few LP modes of the fiber available, and each mode can carry data independently, and it is known as mode division multiplexing. So it is something like this: you have few mode fiber, so this is one mode, another mode, another mode, another mode. Then there are degeneracies also, which I had not talked about. So this mode is in fact has a twofold degeneracy. So it has a group of two modes. It is a group of four modes. This is also group of four modes. So all these modes can carry data independently, and so then this system is known as space division multiplexing system, and this particular one, which uses few mode fiber, it is a mode division multiplex system. Okay, of course, if we want to use this kind of system, then we would like to have amplifier also, and so the conventional amplifier, which is used in WDM system right now, it is not useful for these systems because of the different spatial profiles of these modes. And since these modes have different spatial profiles, then the gains of these modes would also be different. If I use an EDFA, a conventional EDFA for this kind of system, then there are now advancements. There is research going on how we can design an amplifier so that all the modes have same gain. Okay, So we are also working on some of these designs. So these are some of these designs, just to tell you, not going through this, just to tell you what is going on. So these are certain designs of amplifiers with which we can minimize the differential modal gain between uh, different modes of a system. And we have come up with a design which has got French patent also, where we can make the differential modal gain completely zero between the different modes of the system. So I think at this note, I will end my talk, and I would be very happy to answer any questions. And since I have missed several things, so I would advise you, if you are interested, then there are detailed lectures. About 40 lectures are available on YouTube on fiber optics course, which is done by NPTEL. So you can look at those lectures if you are interested. Thank you very much. I would be happy to answer the questions.
Uh, okay, thank you very much, Professor Rastogi. You have touched a very important field of optical fibers and the optical fiber components, and you have said that optical fiber is a lifeline. So today we realize that optical fiber is a lifeline, and we are on virtual platform listening to you. Uh, and bronchoscopy you were talking about today, health of lungs has to be measured because of this corona virus attacking the lungs. So bronchoscope is one of the important device which can give you the health of your lungs. So
Definitely.
yeah, and mobile and fiber keeps us connected. So with these notes, but personally I would like to have your lecture on Bessel functions. You talked about the magic number V less than 2.405, how these Bessel functions how this actually V number is calculated and beta is related to this number. Anyway, sometime again when we will be having your lecture, so that is very
Yes,
interesting.
definitely.
Yeah, I have been teaching this course to PG level students, so it was of great interest to me as well. And the participants who are new to this field on fiber optics must have been exposed to the new terminologies and must have understood that what is going on, how optical fiber is a lifeline nowadays. In 92, I tell you, 1992, I visited Italy, Trieste, Italy, and this field was quite new at that time, and people were talking only the basics of it. And now this field has come a long way that we are talking about now, looking its application in every walk of life. So a very important field you have touched on, and I am very much grateful to you that you accepted our offer to deliver a lecture, and will be having your services in future as well. Thank you very much.
Thank you. Thank you. Thank you so much.
If participants have any query, they can put in chat box so that I can ask. Yes, there is a one query. Uh, possible audio and video signal multiplex in one light signal?
Yes, yes, it is done, because you see, you are listening to me and you are seeing me also. Okay, so it is already there. It is already there. Okay, it is
One another,
embedded
yeah,
together.
yeah, it is embedded together. So how to calculate effective refractive index?
Yes, so if you are given a fiber, then you see, you will have to use Maxwell's equations. You will have to use Maxwell's equations,
Yes, yes.
and then you will have to form wave equation, and will have to apply boundary conditions. It will take at least two lectures.
Yeah,
Okay,
yeah,
but
yeah,
it
yeah.
is, yeah, it is possible. It is possible, and yes, you can find out for a given fiber what modes are possible. Okay, how to label these modes, how to find out the effective index of the mode. Basically, you will have to write down the wave equation, and then you will have to write the solutions of these wave equation in the core and the cladding, and apply boundary condition that will give you transcendental equation. The transcendental equation that you will solve, it is in Bessel functions, that will give you effective index of the mode.
Yes. In the morning inaugural session, I started with a note of Maxwell's equation. Only four Maxwell's equation has changed our world. But Maxwell, in
Yes.
fact, has written many equations and they were reduced to four equations.
Haha.
So that is another chapter I will be discussing sometime again. Okay, thank you, Dr. Rastogi. Thank you very
Thank
much.
you. Thank
Uh,
you very
okay,
much.
your
Thank
tea is due to us, and whenever you will be visiting our campus, it will be from our side. Anyway, we are online, so we cannot serve it, but thank you.
you. Sure. Thank you. Thank you very
Okay.
much.
Okay. Huh? All participants are requested to send the Google form because it will be attendance come feedback form, and your feedback will be important to all of us. So tomorrow we'll be joining at 10 and we'll be starting our lectures. Okay. I hope you must be enjoying the technical sessions. Okay. Have a nice time. Thank you.
organized